Okay, hello, this is Dr. Janes, and today I had a request. Someone wanted to see let's see, we have our high voltage power supply over here that I've used for some of my experiments with the racing coils, and it has our Arduino Uno, which is over here, and I have a bunch of wires going to it. And they're asking about the wire diagram and the source code. Today I'm just going to talk about the source code because that's a pretty complicated thing. And so let's take a look at the source code. Now I believe that this is the latest source code that I wrote. My computer crashed a while back and I had to recover things, and I believe this is the final one that I used. And I actually took an example that I found on the web. I can't remember where I got it from. I know a guy named Nick Gammon, I believe, was talking about some techniques to code faster. And it's possible it came from him or somebody else. And anyway, I took the example and I modified it. So what the deal is with the Arduino is that the normal codes that they use are very slow. They're designed to work with all the different types of Arduinos. You have the Arduino Uno. What do we got here? Then we have the Arduino Mega, and a bunch of other different types of Arduinos. There's probably about 20 different types of Arduinos, and the commands are designed to work with every single type of Arduino, and so they're written to be very compatible with all of them, but they're very slow. And for instance, when you want to do an analog to digital read, it's a very slow process, and when you want to do even the digital write, it's a slow process. And there is people who figured out how to do things fast, but I believe that the codes are only compatible with certain types of ones. Like this is written for the Mega. The Arduino Uno, the cheapest one that we have. And so I'll kind of go through the source code and explain what's going on here as much as I can remember, because it's been quite a while since I wrote this. And so here's our sketch, and there's some comments at the top that I just left there. So I have some variables. I'm setting up some variables, and there's some flags and other values, integer, and I'll get into the code a little bit more, but we have a frequency 1, a frequency 2, a duty 1, and a duty 2. So I actually have 4 pots on the power supply. And there's 2 frequencies. There's a frequency of the carrier frequency, and then I have a pulse modulation frequency. Then I can also pulse modulate. I can change the duty of both of those. I can change the pulse modulation frequency duty, so it can have short pulses or longer pulses. And okay, I just wanted to quickly talk about the different pulse modulations that I'm using in my program. So the first kind of pulse modulation, here we have the carrier wave, and I want to explain that the reason why we're doing this is because FETs don't like to be switched, or any transistor for that matter, has the most losses during the switching time, and so that's why switching power supplies are so efficient, and other things where they switch all the way on and off. So what we're doing here is we're switching just on and off, but the problem is that what happens if you want some kind of analog, something that behaves kind of like an analog signal, where you don't really want full power coming out, but you still want to be able to switch on and off. And so what we're doing here, this is our carrier frequency, and this is a square wave full duty, right? And so what happens is if we want to kind of limit the power coming out of this device, but not try to switch these things in an analog manner, which would be very difficult. Instead, we can switch it in a digital manner. We can delay the on pulse so that there's a certain amount of off time before the pulse comes up, and this pulse can be made narrower and narrower until it's almost zero, and we can do that on the down pulse also. keep on making these. So if you adjust where this turns on so that there's some dead time in there, then it's kind of like a pulse modulation scheme where it can do an analog effect. It can lower the power output without without switching it in an analog way where it's got high resistance, or switching it somewhere in the middle. We're switching it on and off still, but we're just changing the duty cycle of the carrier. Now, I also wanted to make this device pulse modulated because when you pulse it, maybe you don't want it to be on all the time, and when you pulse it, you can get a higher power output for the same power input to the device. It's got some big ass capacitors on there. Let's take a look at the capacitors. They're big ass capacitors, and they can store up a bunch of energy, and so if you pulse modulate it, you can actually get higher pulsed output. You want to make sure not to exceed the power of the transformers, the FETs. But so here's the idea: is that you can have a window where the signal turns off for a certain amount of time, and then it's pulsed on, and so you can change how wide this duty cycle is by making this smaller or bigger. You can make it, if you make it full size, it's just a CW wave going all the way across, and then if you decrease this, it will make this pulse shorter and the rest time longer. And the two different frequencies that I'm talking about is, the first one is the carrier frequency, and the second one is the frequency. This, maybe you don't want to pulse it at 10 hertz or whatever. Maybe you want to change the frequency that this repetitive pulsing happens at. So that's why I have two different frequencies in there. So anyway, I just wanted to clarify those different frequencies and the different pulse width modulation delays. Okay, so let's get back to the program. So that's what these variables are for. And so let's go down through the code. So we have void setup, which is where we're setting up the output pins. I have two output pins, and I'm driving basically two FETs on the board out of phase. I have one on each side. One drives current one way through the coils, and one drives current the other way through the coils. And so they alternate on and off, and they'll both turn off during the when you're not modulating it. So during the unmodulated part of the pulse modulation, they'll both turn off together. And then when they turn on, they'll go up, down like that, create a burst of signal, and then turn back off again. Okay, so now we're setting up to do an analog read, because this is a very slow process normally, and I don't completely understand this. This is part of one of the examples that I used as an example to write this. And I believe that this is setting up the mux for the to read the analog input and getting it ready to read, and then the program, I believe, continues to execute. So these mux commands are setting up the registers and getting things ready. And then I think this is the one that I had to modify, and I found that, see, these other ones above are in binary, and I just used a normal number here because I believe you can put that in as well. And this is what determined, I believe, what pin input that I'm reading. So this, I believe, is AMUX for 3. And then we're doing some more setup. Let's see. Okay, and I believe this is the read portion. And it's setting up the prescalers. Prescaler has to do with when you're doing these processes, they're kind of hardwired into the main clock. The main clock is at 16 megahertz, but you may not necessarily want to take samples that quickly. So you want to, they have things that divide the clock speed down, and so you can take samples less frequently, and there's reasons for doing that. I think the longer you take to do the sample, it's more accurate, but of course it takes more time, and so you have to kind of get a balance there. And okay, So we're setting the universal interrupt, and for some reason that has to be set also. Like I said, I don't completely understand what's going on here, but the example did work. And I tested it out, and it's working in the main device here. So then we go down, and here's our loop. We're going to start the loop, and we're going to check for interrupts. And these interrupts have to do with the pulse modulation, because I'm going into two different modes. I'm either going to be generating a frequency, or I'm going to be generating a flat area where there's no frequency, no output. And that's how you generate the pulse modulation. And okay, so I believe that this is checking to see if it is time. I think pin num tells you that it's ready to read another sample, and so then it will go ahead and try to read another sample. So now it's setting up to do some reading. AMUX, I believe, is pin 4. Okay, read flag, pin number equals 4. Okay, and then we go down here and we're going to do another read. AMUX equals 1, so it's basically the same commands to do another read, and we're going to read pin 1. And then we're going to go down and do another read, and this is pin 2. And then okay, I think what I'm doing here is I'm only taking the reading from you have to kind of balance the timing, because the Arduino is kind of at the edge of whether it can do this or not. So I think I'm just taking the reading of one pin, and then I'm cycling through them at a later time. So I'm not taking all the readings at once. I take one, and then I wait a little bit, and then I take another one, and then I kind of cycle through the different one of 4. And so that's what the this variable here, pin num equals 2, is saying, well, I just took 2, so then we're going to cycle to the next one. Okay, and then here's the last reading. AMUX is set to 3, and so it'll kind of cycle through those. And here's a mapping. The mapping function takes the variables that you want and maps them into a range that you want. And the duty off time depends on not just the duty time, but it also depends on the frequency, because if you have a higher frequency, then it's going to change how much the duty is, how much time it's off. So it's doing calculations for these variables to put into the delays later. Okay, so we set the pin equal to 0, and then okay, so we're coming down here, and here's a for loop, and what this is going to do is this is going to generate our frequencies if it's time for frequency to be on, and the length of the on time is also dependent on the frequency and the duty, and there's some offsets due to delays, due to the stuff above, which is included into here. I is the looping variable, I++, adds 1 every time it goes around. And so this is the command to write quickly to the digital output pins. And so we have digital output pins, and I believe it's 10 and 9 that we're using to drive the FETs. And so not 4, I believe, is turning it off, and 2 is turning it on. It's been a while since I've done this. So we'll set one high, one low, and then we go down to the next cycle. We'll set the other one low, the other one high. and it will do this back and forth, and then when it's done it will set both of them off so they both go low, not 4, not 2. And this port B write command is much faster than digital write. If I used all the digital, the standard commands that come with Arduino, this thing would run so slow you wouldn't be able to do a reasonable frequency and timing properly. So that's what's going on here. And then in order to do the pulse modulation, there's the delay cycle. So it will count that out and do a certain amount of delay based on that. And this is some variable keeping track of that. I forget what that was. Control 1. And then we also have delays due to there's two different pulse modulations, and so I have two different delays accounting for that. And this is what these guys are. And okay, here's our interrupt service, and I believe this is for the A to D. So I think that it's just coming here when it's ready to take another A to D reading, and then telling it go ahead, do that reading. So this is part of the fast analog read, where it's using an interrupt. So I believe that it sets up the registers, the muxes, and then it kind of lets the program execute, and then it has an interrupt. It says, well, when you're ready, come here, and then it will tell it, go ahead, take the reading, and continue. And then you can look in the registers later for the number that it has read. So I believe that that's what's going on. It's been a while since I wrote that, but this is the code, I believe, that did work for me. And that's about as good of an explanation as I have right now. And anyway, so this was a request. Someone wanted to see the source code, so here it is. I went through the whole source code, and if you want to try to play around with that, there it is. And I hope this helps out. This is Dr. Janes, and thanks for watching.